Integration by parts. You have u, v minus the integral of v du. And this is it, fellas. That's all I'm going to put on the board. That's it. That's integration by parts. Now, you're not expected to know what that means or how to use it. That's my job to teach you that. But that is the formula. So what you're going to do, and we're going to just work an example to illustrate how to do it, because integration by parts is really can be really tricky to learn unless you just talk about an example. Let's say you had an integral x times e to the 2x dx. When you see a problem like this, your first thought is going to be, let me try to do substitution and see if I can figure it out, okay? And so I encourage you, pause the video, try to pick a few things to do regular old substitution, and you'll figure out it's not going to work out. The reason it's not going to work out is because, well, the way the problem's constructed is, this is an indestructible function, this e to the x, so as you start taking derivatives of things, it's never going to go away. That's one problem. Second problem is, if you try to choose u to be this up here in the top, you take the derivative of it, you're going to get 2, and you're not going to be able to cancel this x away. So no matter how you choose substitution, you're not going to be able to cancel it enough to get it into a form that you already know how to solve. So some very smart person somewhere a long time ago invented this technique called integration by parts. Okay? The idea is you break this integral up into 2 different parts, and you cleverly define what those parts are, and then you can use this formula that we're going to talk about in a minute and actually solve it. So just work with me here, and I think you'll get it. First thing you do is you define a u, just like we do before. I'm going to define u is equal to x. Okay? The next thing you do is you define a dv. I know this doesn't make any sense, but you do it. And that's going to be, in this case, equal to either the 2x dx. Now I'm going to pause here, and I'm going to explain to you why we chose that. What you're trying to do is you're trying to write this integral in terms of integral of u times dv. Okay, this is what you're trying to do. I've chosen u to be this part, right? And I've chosen dv to be whatever's left over, including the dx. You see, I wrote the dx here. So every integration by parts, you're going to need to start out by defining a u, which is going to be some portion of it, and then you're going to have to define some dv, which is going to be everything else left over. And what you're trying to do is write this integral into this. And really, what you're really saying over here is that if you can write an integral in this manner, the answer is uv minus integral of v du. Okay, which is what we wrote here. Okay, so I'm going to erase this for now, but I just wanted to tell you why we picked u and dv the way we did, and so on. So I'm not going to explain any more theory. We're just going to go on and work the problem. Once you write your u and your dv, the next thing you need to write is you need to figure out what du is, because notice the answer is going to have a du in it. Just work with me here. Du with respect to x is equal to 1. If you just take the derivative of this, you just get 1. So then du is equal to dx. Okay? So that's easy. You've got that. Now, you're also going to need to know what v is, because v is in the answer as well in 2 places. But here you have dv. So in order to find v, okay, what you do is you integrate both sides of this. Okay? So if you think about it, the integral of dv is equal to the integral of e to the 2x dx. You know, in algebra you can do the same things to both sides of the equation, and that's okay. As long as you do it to one side and you do it to the other side, you've not changed anything. Here, all I've done is I have this sort of this differential equation is really what it is, and I've integrated both sides of the equation. I haven't changed anything, I've just integrated both sides. Now the integral of dv is just going to be v, which is what I'm trying to find. Okay? The integral of this right-hand side is what I need to do in order to actually figure out what v is. Now we've done a problem very similar to this before. Okay, the answer to this is going to be 1 over 2 e to the 2x. Okay, I encourage you to pause the video and do this integration by yourself. We've done a problem very similar, maybe even the exact same problem in the section earlier when we tried to integrate exponentials. So this should not be a shock to you. It's just I don't want to clutter up the board with a bunch of stuff here because you're trying to learn a new concept. This integral, you know how to do it. You could just define this exponent as as another, substitution variable. You could use s, or you could use u, you could use whatever, and use integration by substitution, and you will find that this is the answer. So go back to the other section if you don't understand that. But you see, what we have here is 4 important pieces of information. We have the initial u we picked, we have the initial dv that we picked, and then from that we found what du was equal to, and from this we found what v was equal to. So we have 4 very important pieces of information. U we have here, v we have here, we have an integral sign, and then we have v we have here, and du we have here. So we have all the pieces to find the answer. So the answer to this integral is uv minus integral v du. So the answer is u, which is x from here, v, which is 1/2 e to the 2x minus the integral of v, which again is 1/2 e to the 2x times du. Du in this case is just dx. Okay? So we have some junk out front and we have another integral to do. Okay, so let's clean it up a little bit. What you'll have is x e to the 2x over 2, that's all this is, minus this 1/2, I'm going to pull it out, 1/2 integral e to the 2x dx. Now look, this integral, e to the 2x dx, it's the same integral that you did here. It's the same integral that I told you that you already know how to do because we've done an exact same integral in a previous section of the class. The answer we already wrote down here. So we can finish this problem right now. X e to the 2x over 2 minus 1/2. This is the 1/2 that was written in front. Now we got to figure out what this integral is. The answer to this integral, we've already calculated it. It's 1/2 e to the 2x. Don't forget, anytime you do integration, you got to add that constant. So in the end, the answer to the problem is x e to the 2x over 2 minus e to the 2x over 4 plus a constant. Now I want to back up and I want you to let this soak in. What you're trying to do is you're trying to define in an integral a u and a dv, and you're trying to write an integral as u dv. The answer I've given you right here, which is uv minus the integral of v du. Now the point of this problem is if you choose the integral, if you choose your u and v properly, then what you'll end up with is something out in front, and you'll end up with another integral that's easy to solve. And that's the only reason that this method's useful. You break it up into parts. So you get the first part, sort of an answer, and you get another integral that hopefully is easier to solve. If it's not any easier to solve, well then this method is useless. Okay? We looked at the problem, and we picked a u, which was over here, and we picked the dv, which was the rest of it, okay, so that we could put it into this form. And then in order to find du, we took the derivative of this. In order to find v, we just took the integral of this, okay? And then we plugged it into this formula, uv minus integral v du. We had some stuff in the front that was easy to do, and then we had another integral to solve, and after we solved it, that was the answer. Okay, now I'll give you one hint. A lot of the integration by parts problems that you're going to see on tests and in the book, a lot of them, if not maybe almost all of them, involve an exponential. Because if you try to do regular old substitution with formulas with integrals like that, you're going to run into problems because those exponentials are kind of indestructible. You can't get rid of them, so it's very difficult to cancel them. Okay, you got to do it like this. And so, if you choose your u, the reason this really works is if you choose your u to be this, and you take the derivative of it here, it goes away. This x goes away. Okay, and by doing it that way, you can end up making the problem simpler. I don't want to belabor it too much more because really you're gonna understand, I think, more what I'm saying as we work additional problems. We're going to work more problems, and I think you'll understand the pattern that I'm looking at. I mean, I could sit here and tell you the pattern of what to look for, but it's not going to make much sense until you sit down and you start working a lot of problems and start figuring out, oh, well, I need to go ahead and define it like this so that this will cancel later on. Okay, and then it'll make a little bit more sense. Okay, so the next problem we're going to do is going to be the integral of x times the sine of 4x dx. Now, I'm going to give you a couple hints on when to use integration by parts. Okay. In the other problem we just had a minute ago, we had x to the e to the 2x dx. You see, we had x or some polynomial in x times an indestructible function, which is an exponential is like an indestructible function. In this case, we have x or some polynomial of x, and we also have it multiplied times an indestructible function. Anytime you see like x or x squared or x cubed or something multiplied times an indestructible function like sine or tangent or cosine or e to the whatever, then you're going to need to use integration by parts. Okay, that's my advice to you most of the time. And furthermore, remember in the previous problem we chose our u to be equal to x and our dv to be everything else. Well, that's going to be my advice in this problem. Use u to be the x that's out in front, and then dv to be everything else. And as you work problems, you'll see why that works out. But I'm trying to give you some helpful hints up front. So if I say u is equal to x, okay, and then dv is equal to sine of 4x, okay? So u is equal to x, dv, and I forgot to write my dx over here. dv is everything else, okay? So then, first thing I do is I take the derivative. du is equal to dx, okay? The derivative of both sides. And then v, we will get by integrating this. Is the integral of sine of 4x dx, okay? Now again, the way you would do this is to use a regular old substitution to do this integral. We've done problems very, very similar. In fact, we've probably done the exact same problem in another section. So I'm going to give you the answer just so you can get the big picture here. This is 1/4 times the negative cosine of 4x like this. Okay? So then v is the negative comes out negative 1/4 cosine 4x. The reason I can do these in my head is because I know from experience that the 4 is going to be coming out, and it's going to be 1 over that, and then I'm going to be left with the regular old integral on the inside. But to do it right, you would do regular old plain Jane substitution just like we did in the previous section of the class. We see now we have u, du, v, and dv, and now we can solve this problem. Okay? So the integral is equal to u, v minus the integral of v du. U is equal to x, right? V is equal to this stuff, so it's negative 1/4 cosine of 4x, okay? Minus the integral of v, which is again negative 1/4 times cosine of 4x times du. Du is just dx, like this. So it's going to be negative x times the cosine of 4x over 4. I just simplified this. I got a negative sign and this stuff on the top, 4 on the bottom. Negative times negative gives me positive 1/4 times the integral of cosine 4x dx. Now notice what we have here is we've got the problem into some part of the answer here plus some integral that we know how to do. This integral is already been done before. We've done it in the other section of the class on trig integrals, and the way you do it is you do it by substitution. You set 4x equal to u, and you do all the stuff we did for substitution and get the integral in terms of u and integrate it, and what you will see in the end is something that's going to look pretty familiar. This 1/4 comes from what's in front. When you do this integral out, what you're going to get is 1/4 times the sine of 4x. And then, of course, anytime you do this integration, you got a constant off in the end. I encourage you to go ahead and practice this and do it again. If you go back to the section of this particular DVD on trig integrals, you will see that we've done a problem, probably the exact same problem or something very close. So to finish it off, you have x times cosine of 4x over 4 plus the sine of 4x over 16 plus a constant. And that's the answer to the problem. You see, the trick is knowing what to set as u and knowing what to set as dv, and then knowing the mechanics of coming down and doing this stuff here. And then really you do uv minus integral v du, and really that's the answer. But I'm giving you a hint here. Most of these integration by parts problem is gonna have some x or some x squared, x cubed, or something like this, and then you're gonna have an indestructible function. What I mean by indestructible is if I keep taking derivatives of this, it's never gonna go away. Because you see, the derivative of sine is cosine. But then you take the derivative of cosine, it's negative sine. And then you're kind of back where you started. You keep taking the derivative, it never goes away, okay? That's why you need to use integration by parts. So when I see this, I choose whatever's left over, including the indestructible function, as my dv, and usually that will get you on the right track. That's the best piece of advice I can give you. And most of the time, these integration by parts problems are in that form. We're going to do one more problem. It's going to be a little bit harder, and you'll see what I'm talking about. What if you have the integral of x squared times cosine of 3x dx? Well, here's what I'm talking about. You've got x squared, which is x, some function of x like this, and then you've got an indestructible function. So I know I'm going to need to use integration by parts, and furthermore, I know that I'm going to set u equal to x squared, this thing here, and I'm going to set dv equal to whatever's left over, cosine of 3x dx, because I have to include the dx. Now to do this part, I'm going to say du is equal to 2x dx, right? The derivative of this is 2x, and I'm just moving that dx over like I always do, because it's really du divided by dx, and then I can move that dx over. And then to find v, it's just going to be the integral of cosine of 3x dx. I just have to integrate this. Now again, the way you do this is you've got to use integration by substitution. You'd set u equal to what's in here, and you'd go through the motions, and then in the end what you would get would be 1/3 times the sine of 3x. That's what v is equal to. Okay? Now I am skipping a couple steps between this and this, but it's only because if you go back to that other section of the class, I've done problems exactly like that, and I think that if you go back, you'll be able to convince yourself that this is right. So now we've got everything set up. The answer is equal to uv minus integral v du. Okay, so let's do that. Okay, u is x squared. V is 1/3 sine of 3x. Okay? That's uv minus the integral of v, which is 1/3 sine of 3x. du is 2x dx. 2x dx. So let me rewrite it. What you'll have is x squared times the sine of 3x over 3 minus, I'm going to pull this 1/3 out, and I'm going to pull this 2 out. So I'm going to have 2/3 times the integral of x, that comes from here, times the sine of 3x dx. Now this is why I said this problem is a little bit difficult, a little bit more difficult. When we do this, we get some function here that's part of the answer, and we get another integral. And this integral is indeed a little bit simpler than the first integral, because it's a first power of x instead of a second power of x. But notice that this form is the exact same form that we of an integration by parts. Okay, so this, you should know by looking at this, you've got x times another indestructible function. You're going to need to do integration by parts again just to get this answer. So it's a little bit of a going down the rabbit hole, okay? You've got a function, you don't know how to do it, so you do integration by parts, and you get another integral. But you still don't know how to do that one, so you've got to do integration by parts again. But notice that each time you do it, this power of x gets less and less, okay? And if it were x to the 5th up here, you'd have to do integration by parts 5 times in order to get the answer. But since it's x squared, you're only going to have to do it twice. I know it's not exactly probably what you wanted to hear, especially on the test, but it's true. So I'm going to change colors, and now we're going to work strictly with this integral. Okay? I'm going to set u, and I'm going to actually do it over here. I'm going to set u equal to, what do you set it to? X, just like we did before. dv, I'm going to set equal to whatever's left over, which is sine of 3x dx. Okay? So then now I've got du is equal to dx, right? And v is just equal to the integral of sine of 3x dx. And again, this integration you should be able to do by substitution, and we've done it before. So it's 1/3, it's actually going to be negative 1/3. Negative 1/3 times the cosine of 3x dx. Okay? Now I want to make sure that you're clear that when I'm skipping steps like this, I don't want you to do that. I'm doing this for board value here, not to have too many things to clutter the big picture. But in order to do this integration, you're going to need to define a u, and you're going to need to go in and do that substitution business, and you'll find out that you'll get this in the end. And we've done that before. So now I've got everything I need to solve this integral. So coming back over here, actually let's don't do that for clarity. Let's keep it right under here. We're going to have uv minus integral v du. U is x, v is this, okay? So I'm going to have negative 1/3 cosine of 3x, okay? Actually, there's no dx on the end here. I've already done the integration, okay? So we'll do it like this, minus the integral of v, which is negative 1/3 cosine of 3x. That's v, and du is just simply dx. I'm going to draw a little divider through here like this. So it's uv minus integral v du. That's all we've done. Let's rewrite it. We'll have negative x times cosine of 3x over 3. Negative times negative gives me a positive 1/3 times the integral of cosine 3x dx. Now, you see I've got another integral to solve, but you see this one's even simpler. So we started here, we had another integral to solve, but we still had to use integration by parts, and when we did it on this one, we ended up with another integral to solve, but this one's even easier. So this one, I'll just tell you, is equal to 1/3 times the sine of 3x. Okay? So you see we've got this, and then we've got this, and then we've got this, and we need to make sure we catch it all, otherwise the whole problem is going to be wrong. So I'm going to switch colors again, and we're going to say the answer is going to be equal to x squared times the sine of 3x over 3, that's this term, minus, you've got this 2/3 hanging out here, don't forget, and the 2/3 is multiplied by this integration, which is everything else. So you've got to put a big bracket here, because everything else that followed was multiplied by 2/3. Inside here, I've got negative x times cosine of 3x over 3, okay, plus, now I have 1/3 times the result of this, which was this. So 1/3 times 1/3 is 1/9. And then the answer here was just the sine of 3x. Okay? And so then in the end, you'll have x squared times the sine of 3x over 3 minus, actually it's going to be plus, negative times negative gives you positive, 2x cosine 3x, like this, over 3 times 3 gives me 9. And then you have minus, because negative times positive gives you a negative. And you're going to have a 2 on the top, 2 over 27, because you have 27 here. 3 times 9 gives you 27. Sine of 3x. Okay. That is the answer. Now don't forget, you always have to add a constant. So you'll get points off if you don't do that. This, I have to admit, was a pretty complicated problem, and that's why I wanted to do it last, obviously. You have a function in x, polynomial, times an indestructible function. You had to define your u and your dv to get you a little bit farther along, but in the end you had a function that you still didn't know how to solve exactly. You had to use integration by parts again, do the whole thing again, and you end up with an integral here that you know how to solve quite simply using regular old substitution, which was this. And then you just need to make sure when you write it all down that you get everything multiplied by everything as we've talked about here, and you'll get the right answer for integration by parts.
Learn anything at mathandscience.com.